Hey everyone, welcome to this explainer. Today, we're going to completely transform how you visualize and honestly really understand operations with integers. If you've ever found yourself just kind of confused by the rules of multiplying negative numbers, or wondering why subtracting a negative actually feels like adding a positive, well, you're in exactly the right place. We're going to unpack the underlying logic of this chapter together so you don't just memorize rules, you actually get them. So here's what we're looking at today. We'll start with some puzzles and number games, then move into visualizing moves and tokens, cracking the multiplication code, diving into division and distributive properties, and finally, wrapping it up with some real-world integer applications. Let's get right into it.
All right, part one, puzzles and number games. We're building that intuition first.
So here's a fun one, Rakesh's puzzle. He says, I've thought of two numbers. Their sum is 25, and their difference is 11. Now, without writing down any complex algebra, seriously, don't write anything down. Try to guess the answer in your head right now. What two numbers add up to 25, but when you subtract the second from the first, you're left with 11? Got a guess? Let's figure it out. It's actually super clear when we map out our guesses, just using basic trial and error, right? Say we start with 10 and 15. Well, the sum is 25, sure, but the difference is -5. Not quite. What if we try 20 and 5? Sum is 25, difference is 15. Okay, getting warmer. Finally, let's test 18 and 7. Sum is 25, and the difference is exactly 11. Boom, they fit perfectly. And you know what this proves? It proves you already have the foundational logic to understand integers, literally just by playing around with values. Moving on to part 2, visualizing moves and tokens. We're bringing math into the physical world. It's actually fascinating how we can take abstract numbers and anchor them to things we can physically move. Think of a carom board. Imagine a coin starting right at 0. A positive integer is simply a strike moving the coin to the right. So if your first strike moves the coin 4 units right, and your second strike moves it 3 units right, your final position is clearly 7. It gives us this brilliant physical sense of addition, capturing both the distance moved and the direction. And naturally, if we were striking to the left, we just use negative numbers. Now, another way to look at this is by using physical tokens. We can use green tokens for positive numbers and orange tokens for negative ones. It's a super simple but incredibly effective visual language. And this brilliantly brings up the concept of zero pairs. See, when you put a green positive token and an orange negative token together, they just cancel each other out to equal 0. This physical model shows us that taking away negative orange tokens from a group is the exact same mathematical action as adding positive green tokens. It takes that classic, sometimes confusing double negative rule and turns it into a logical, physical action that makes total sense. All right, part 3, cracking the multiplication code. It's time to detect the hidden patterns. Okay, I want you to really look at this sequence. Notice how we're dropping the first multiplier by 1 every single time. 3 times -3 is -9, 2 times -3 is -6. We're essentially just adding 3 to our product at each step down. 1 times -3 is -3, 0 times -3 is 0. So what happens when we drop down to -1 times -3? Well, if we follow that exact same mathematical pattern of adding 3 to the previous result, the answer literally has to be +3. Step by step, it suddenly makes perfect logical sense why a negative times a negative becomes a positive. It's not just some random rule you have to memorize, it is an unbreakable pattern. And while we're talking about multiplication, check out this fantastic little mathematical shortcut. 14 times -5 equals -70. But if we totally swap the order, calculating -5 times 14, it still equals -70. This is the commutative property. It basically tells us that swapping the multiplier and the multipliand doesn't change the magnitude or the sign of the product, like at all. You can calculate it whichever way is easiest for your brain. Okay, part 4, division and distributive properties. Let's formalize these hacks. So the distributive property is honestly one of the most powerful tools in your entire math toolkit. It lets you break down complex multiplication problems into smaller, much more manageable bite-sized additions. Basically, multiplying a number a by the sum of b and c is the exact same thing as multiplying a by b, multiplying a by c, and then just adding those two products together. It distributes the multiplication across the addition seamlessly, even when negative integers are in the mix. And what about division? I know it can seem daunting, but division isn't some totally scary new concept with a completely different set of rules for integers. We can just reframe it. If you see negative 100 divided by 25, just ask yourself, what should be multiplied to 25 to get negative 100? It's literally just asking you to find a missing multiplier. Since we know a positive times a negative equals a negative, the answer absolutely has to be negative 4. Simple as that. Which brings us to part 5, real-world integer applications. Because why does all this actually matter? Let's take a look at Mala's exam scenario. She's taking a 50-question multiple-choice exam, and the stakes are pretty high. She gets a positive integer of 5 points for every correct answer. But here's the catch. She's penalized with a negative integer, -2 points for every single wrong answer. So here's the situation. Mala got exactly 30 correct answers and 20 wrong answers. I want you to just quickly pause and try to calculate her final score in your head right now, using the integer multiplication rules and addition properties we just went over. Go ahead, give it a shot. All right, did you get 110? Here's how it breaks down. She gets 150 points for the correct answers, 30 times 5, but then we have to add the negative integer points from her incorrect answers. So 20 wrong answers times -2 gives us -40. 150 plus -40 leaves her with a pretty triumphant final score of 110. Or let's consider a completely different real-world situation, something like an elevator descending into a mine shaft. The elevator is moving downwards at a rate of 3 meters per minute, and because it's moving down, we represent that speed as -3 meters per minute. It starts exactly at ground level, our 0 point. So if it descends for exactly 1 hour, meaning 60 minutes, where is it going to be? We can just use integer multiplication to predict its exact future location. 60 minutes multiplied by -3 meters per minute gives us a product of -180. That means the elevator will be exactly 180 meters below ground level. The math perfectly models both the magnitude of the distance and the direction. Pretty cool, right? From visualizing moves with Karam coins to tracking elevators deep underground, integers really give us the language to describe the physical world with absolute precision. And it kind of leaves you wondering, if simple integers dictate everything from the points on our exams to the massive machines we write in, what other fascinating invisible mathematical rules are operating in the background of your daily life right this very second? Keep looking for those patterns. Thanks so much for joining me on this explainer, and definitely keep learning.